Good morning. We're Group 36, and today we'll be discussing our senior design project, the multi-purpose device controller. Our group members consist of Kenny Dow, who is a computer engineering major, myself, Johnny Blanc, who was also a computer engineering major, and Jason Jean Lewis, who was also a computer engineering major. And lastly, Mohammed Talib Hamed Rashid Al Fahadi, who is an electrical engineering major. Our motivation for this project was recognizing the demand for a versatile controller that can connect to multiple platforms. Being gamers ourselves, we wanted to address common issues such as stick drift, unintended and gradual movement of a gaming controller joystick, often caused by wear and tear on internal components, leading to challenges in precise control. So overall, we wanted to enhance the gaming experience by providing a reliable and responsive controller. One of the key aspects of our controller's design is its connectivity. We wanted to ensure a hassle-free experience for gamers, which led us to integrate Bluetooth technology. This not only eliminates the need for the cumbersome cables, but also enhances the overall user experience. Now gamers can seamlessly connect to their favorite consoles without any hassle. Goals and objectives. Our main goal is to design a durable controller with universal compatibility across multiple gaming platforms. Objectives. As mentioned before, we want to focus on eliminating stick drift. By introducing the Hall effect joystick mechanism, we believe that this will effectively eliminate stick drift issues, ensuring precise and reliable input during gaming sessions. Multi-console compatibility. We want to create a controller that seamlessly connects to a variety of gaming consoles, providing users with a versatile gaming peripheral that adapts to their platform of choice. Bluetooth connectivity. By introducing Bluetooth technology and wireless connectivity, we believe that this will enhance user mobility and reduce cable clustering for a more convenient gaming experience. Here are some of our stretch goals. Develop software enabling users to personalize controller settings and configurations. Enhance compatibility across a broader range of gaming consoles. Design rubberized exterior to enhance grip and handling comfort. Our current specifications are as follows. Operating time for our controller will be 5.6 hours. Recharge time, 1.5 hours. We'll be charging our controller through USB-C port. Connectivity will be USB-C/Bluetooth Low Energy. Bluetooth range is currently 10 meters.
Here's an overview of our main hardware components. We will go into greater depth on each one later, but for our microcontroller unit, we were considering the ESP32, STM32F11, and the Arduino Nano. We decided on the ESP32 for its ease of use and Bluetooth capabilities. For our power source, we were in between a lithium-ion battery, lithium polymer battery, nickel metal hydride battery, and a power bank. We decided on the lithium polymer for its size, power output, and protection circuit. For the analog sticks, we were considering a Hall effect joystick or just a regular one. We ended up choosing the Hall effect for its longevity. With the LEDs, we were considering the Adafruit 5050 RGB LED or the full color top LED. We chose the Adafruit because of how many LEDs we could get in bulk. Here's our hardware block diagram. We have our USB-C charging our rechargeable battery, which goes through a voltage regulator and feeds power to our MCU. The MCU sends signals to the LEDs, speaker, and whatever device it is connected to. The mic, buttons, and joystick send signals to the MCU as inputs. In terms of who is responsible for what, I am in charge for the speaker, mic, and LED calibration. Mohammed is overseeing the battery and voltage regulator. Johnny will be ahead of the button and joystick configuration, and while Kenny is overseeing the general programming for our MCU. Onto our microcontroller unit selection, we decided on the ESP32 for the following reasons. Built-in Bluetooth. This is helpful in terms of getting us to that universal compatibility we were looking for. Powerful processing, low power consumption, open source friendly, which was a major factor in choosing this one. Easy ways for finding solutions to any problems we may run into with such a large community and all of the libraries and tutorials that are out there. It was cost effective and future proof with the support for the latest Bluetooth standards, ensuring compatibility with any upcoming devices. Here is the side-by-side comparisons for each. Some key things to note are the processor speed, the RAM, and the wireless connectivity options. The processor speed on the MCU is much faster than the other two options, and it has much better wireless capability options than the other two options as well. Onto our analog stick selection, we went with the Hall Effect joystick for the following reasons. To ditch the drift, no physical contact means eliminating stick drift, a common issue with potentiometers and most controllers. Enhanced durability, magnetic sensing resists wear and tear, extending controller life and reducing repair needs. Greater accuracy, it has a higher resolution compared to other potentiometers, leads to smoother and more nuanced control, and lower latency. Less physical interaction minimizes signal noise, potentially reducing input lag. Here is a side-by-side comparison of the two. Some things to take note of are the rotary mechanism using a magnetic sensor and the longevity of the analog stick.
Through selection, we had to take into consideration that we're designing a gaming controller, which means that we needed an extended gameplay time. Our MCU consumes an average from 250 to 300 milliamps per hour. So an 1800 milliamps per hour battery will give us at least 5 hours of gameplay time. We needed something consistent and reliable, and we found that lithium ion and lithium polymer will give us that option. The design needed to be lightweight to ensure comfort for the user. We also looked for rechargeable options because we didn't want to deal with any elimination or replacement of batteries. Also, per week's recommendation, we ensured that we have a safety IC on our battery to avoid the problems that we're going to have later on the PCB design. So we selected the lithium polymer LP653042. The capacity of the battery is 1800 milliamps and the weight is 46 grams. It costs around $10 to $15. The environmental impact of this battery is low because it's rechargeable. Usually there's more impact of the disposable batteries. Our battery operates in a temperature from minus 20 to plus 60 Celsius, and it has a protection from overcharge and discharge and short of circuit protection.
Onto our LED selection, we went with the Adafruit RGB LED for the following reasons. Because it's addressable, we are able to set a color for each LED individually or all of them as a whole to indicate battery life, charging, connecting, and whether it's on and off. Bulk shipping, it comes in a pack size of 10, which was more cost effective for us in the long run. And power consumption, it runs on 10 watts, which works in conjunction with our other components and the output of our battery. Here's a side-by-side comparison of the two. The main thing to note would be the power consumption mainly.
There are numerous approaches we could have taken to develop this controller from the software perspective. Let me walk you through our thought process. When it comes to the wireless communication of our controller, BLE stood out as a clear choice. Its low latency ensures your actions translate to the game in real time, offering a smooth and responsive experience. Additionally, BLE's power efficiency translates to extended gaming sessions, while its wide compatibility allows seamless connection to various devices like PCs, tablets, and smartphones. Built-in security features safeguard your data privacy during gameplay, and BLE's simple integration simplifies the development process. Furthermore, BLE adheres to the latest standards, guaranteeing future-proof compatibility and protecting your controller from being obsolete. Finally, BLE's low cost enables the creation of affordable gaming controllers without compromising on performance. Wireless communication and controllers come in many different forms. Here's the breakdown. BLE offers low latency for smooth gameplay, long battery life, and broad device compatibility, making it the clear winner. While Wi-Fi offers longer range, moderate to high latency can lead to noticeable lag. It also has higher power consumption, limited device support, and higher cost. And lastly, for radio frequency, performance, compatibility, and security vary greatly depending on implementation. Here's why we chose the C language. C grants unparalleled access to your controller's hardware, ensuring the real-time responsiveness of buttons, joysticks, and sensors. Being a compiled language, C boasts minimal overhead, maximizing efficiency and minimizing latency for smooth, lag-free gameplay. Additionally, C provides a wealth of open-source tools like compilers, debuggers, and libraries, streamlining your development process. Furthermore, C's long history and ongoing development guarantees stability and compatibility with the ESP32. You also gain access to a large, supportive community and abundant resources thanks to C's prevalence in professional game development and embedded systems. Finally, choosing C is a future-proof decision, ensuring your controller's longevity and adaptability in the technology landscape. Among the available options, we opted for C due to its superior performance, direct hardware access, and efficient memory management. C offers high performance compared to MicroPython and Arduino C++, ensuring our controller operates swiftly and efficiently. Additionally, its direct hardware access allows for more precise control and optimization. While memory management in C requires manual intervention, it provides better control over resources compared to the automatic garbage collection in MicroPython and semi-automatic management in Arduino C++. Moreover, the vast community and resources available for C facilitates faster troubleshooting and development. Despite its manual error handling, C offers high portability, making it an ideal choice for our project. The controller's initialization process begins with profile selection. Upon powering on, the user can hold a designated button, such as A, to specify the console mode. Subsequently, the controller determines the connection type, wired or wireless. If a wired connection is detected, the handshake process commences immediately, establishing communication protocols. In the case of a wireless connection, the controller actively scans for nearby devices before initiating the handshake. The handshake serves as a negotiation phase, ensuring both the controller and the connected device agree on communication protocols for seamless data exchange. Following successful connection and initialization, the controller enters the operational phase, constantly reading and transmitting user data to the console. Here we tested the ESP's ability to connect via BLE. Upon boot up, the serial monitor tells us that the ESP has started and is ready to pair. We then connected to our PC and were able to exchange data. Achieving accuracy on our controller hinges on two key techniques, polling and dead zones. Polling continuously checks the state of each input, guaranteeing responsiveness and gameplay. This straightforward method ensures every button press and joystick movement is registered instantly. Additionally, dead zones are implemented around the joystick center to filter out minor unintended movements. This helps eliminate false inputs and improves the user experience.
NIMBLE. NIMBLE is an Arduino library specifically designed for Bluetooth Low Energy applications and offers several advantages for BLE-enabled devices, which in our case work in conjunction with the ESP32 microcontroller. The first advantage NIM-BLE provides is its efficient handling of BLE communication, resulting in lower power consumption and extended battery life for compatible devices. Another advantage is its small memory footprint, which is crucial for embedded systems like the ESP32, allowing developers like us to conserve resources for other tasks and functionalities. Finally, NIM-BLE's compatibility with the ESP32 microcontroller ensures seamless integration and optimal performance, leveraging the ESP32's dual-core architecture and built-in Bluetooth support to deliver reliable BLE communication. Other notable advantages of the NIM-BLE include the following: comprehensive API, facilitates BLE functionalities; security, ensures data protection during wireless communication; flexibility, customizable BLE profiles to suit gaming controller requirements.
For our power regulation schematic, we have three main parts: the USB-C connector, charging circuit, and voltage regulator. On the far left, we have the USB-C connector. We decided to go with the USB 4105 GFA as it's compatible with multiple devices since we're using a gaming controller. We've also decided to use this USB-C connector because we're capable to transfer data and use it for charging purposes. The USB-C will be directly connected to our programming circuit and MCU, providing data and programming interface for the developers. For a voltage regulator, we chose TBS 628040 DLCR. It's gonna step down the voltage from 3.7 volts to 3.3 volts. That's mainly gonna be going to the MCU. The MCU is gonna power all the peripherals. Other than that, this voltage regulator has high efficiency step down. It provides an output current of up to 750 milliamps, and this is the efficiency graph of it. As you can see, the color in the blue is the voltage we're using, which is 3.6 volts. This is our voltage regulator circuit. On the left we have a typical application from the data sheet, and on the right we have our circuit in the PCB schematic. So we have 8 pins. We didn't use 2 pins, which are mode and stop. Dr. Weeks recommended that we connect them to a 0 ohm resistor and ground them. These 2 pins are used to stop the current from flowing and also control how much current is flowing through the regulator. And since we are using a fixed current, we didn't need to use them. For our charging circuit, we went with MCB73831. It's programmable and the current varies from 15 to 500 milliamps. For most of the time, we're going to be using 500 milliamps. It has LEDs to indicate the charge status, and it also has a high accuracy for the voltage regulation. So this is our charging circuit on the left, and we have multiple LEDs. The first LED will indicate if it's connected to USB-C power charger or a power outlet, and it's going to indicate a yellow color. If the battery is not full, the red LED on the top will turn on, which will indicate that it's charging, and whenever it's full, we have the LED on the right to indicate that. Furthermore, we have the 2K ohm resistor, and if you see on the down right, we have the equation for that. It indicates how much current we're getting from the circuit, and 2K ohm resistor will give you approximately 500 milliamps, which will provide power for the MCU and the LEDs. So this is our overall PCB schematic. We have on top the power regulation system. We have the USB-C connector, charge circuit, and the step-down converter. On the down left, we have the LEDs, which we're going to be drawing current directly from the charge circuit. Other than that, the step-down converter is going to be providing power to the MCU, and the MCU is going to be providing all the power needed for the rest of the components. This is our PCB layout. We focused mainly on component placement. We have the analog joysticks, the buttons on the far right and far left, and we have shoulder buttons on top. We mainly put power components and programming circuit in the middle with the rest of the capacitors and resistors, and we have LEDs also towards the middle to the right and left.
Budget and bill of materials. This is a breakdown of our components, their cost, and our budget. So far, we spent about $208. Our total budget was around $600. So we currently have $392 remaining. And we're very confident that this should suffice for the rest of the things that we need for our project. The final component will consist of a 3D printed encasing, which will house the PCB and some internal hardware components. Division of work. We decided to distribute our task in the following way. PCB design. Muhammad was the primary, Jason the secondary. Component specification and ordering. Jason was the primary, Muhammad the secondary. Analog stick and button calibration. John was the primary and Kenny the secondary. Bluetooth connectivity. Kenny was the primary, Jason the secondary. Microcontroller programming. Kenny was the primary, John the secondary. Hardware assembly. Everyone contributed equally. Battery regulation. Muhammad was the primary, Jason the secondary. This concludes our presentation. Thank you so much for your time.